everyone. We're glad to welcome everyone at our next edition of Virtual Chai Chat. My name is Gulshan, and I would like to introduce you to our speaker today, PJ Hoke. Hi, PJ.
Hi, Gulshan. Thanks for having me on.
And we have our second guest, Ujan, and PJ will introduce him a little bit later. Hi, Ujan.
Hello.
So I want to introduce PJ to everyone. PJ Hoke is now teaching English in Kashi, and he also is a presenter and leading a lot of program in American Corner Kashi. And he's an undergraduate student at the University of Chicago. He studied math, quantum physics, and quantum engineering. He has experience working with top quantum technology researchers in university, as well as with business leaders trying to understand how quantum technology will change the global economy. He is also, as I already told, very actively involved in American Corner Kashi activities. So please to type your questions in the comment sections during the presentation, and PJ and Ujan will answer your questions as usual. So PJ, thanks so much, and Ujan, thanks so much for joining, and I'm leaving you here, guys. Thanks so much.
Yeah. Thank you so much for having us. And I hope that for this presentation, we will strive to give an introduction to quantum physics and quantum technology. It does not require any prior experience in physics at all. We will be talking in plain English at an intermediate level, just trying to learn about what quantum physics is and what it could mean. And as Gulshan said, today, below me, I'm joined by Ujan Purokayastha, and he and I were both students in quantum physics at the University of Chicago, and he is now continuing his studies in a PhD program in quantum physics. And so I studied this as an undergraduate, as well as did research as an undergraduate, but Ujan is really the expert in the field. So I had him come on to help me and present a little bit about his experience as a graduate student in the US studying quantum physics. Yeah, so Ujan, thank you for joining, and we'll get right into the presentation.
Yeah, so thank you for having me.
Yeah, this Chai Chat, I said, is an overview of quantum physics and technology. So what does that mean? First, let's talk a little bit about me. Gulshan gave a wonderful introduction. Now I am living and working in Kashi in Uzbekistan. I've been here for just over 3 months, working at the Kashi State University, as well as the Kashi branch of TIAMI, and at the new American Corner Kashi. But what about me and my family? Well, I have 3 brothers, and you can see them in this Christmas card here. My family lives close to Chicago in the state of Illinois in the US, and my wife Madeline and I both studied at the University of Chicago. I studied, as Gulshan said, quantum physics, quantum technology, and math. My wife Madeline studied biology and neuroscience and studying to be a doctor now. We are both in Kashi. Some of my hobbies, what I like to do outside of math and physics, I love running, beekeeping in the US. My wife and I are part of a team associated with the University of Chicago, and we do a lot of beekeeping. We have our own bees, we produce honey, and it's a wonderful time. Traveling, obviously, as I am now very, very far from the US, and cooking. I have really enjoyed cooking here in Uzbekistan and trying all the different foods. By far, osh, plov is my favorite, probably mantı afterwards, and samsa are obviously delicious. So let's start talking about physics. And I titled this My Path in Physics. And I thought this would be helpful for anybody watching who is interested in physics. As an English teacher at university now, I have many students who come to me and ask, how do I get involved in physics? How do I get involved in math? What are resources I can use? And so I figured I'd talk a little bit about my path, how I studied physics. In school, I didn't study physics, but I did study a lot of math. So this is like 9th through 12th grade, I had no physics experience before going to university. And then in university, I decided to major or to study in quantum physics because for me, I thought of it as a first step. My goal, I suppose, was to learn and to know as much as possible. And I decided to study physics, and specifically quantum physics, because quantum physics is the study of the smallest things. And I figured if I wanted to know everything, I have to start very small. And so that's really how I decided on physics. Nothing more interesting or thoughtful than that. And so I did a 4-year undergraduate study in math and physics, but I decided to not pursue graduate school. And so this is where Ujan and our paths diverge a little bit, as Robert Frost would say. He now is continuing on the path of a physicist. He's doing high-level theoretical and application research, interested in a future working as a physicist, whereas I decided on a different path. And so having us both here, hopefully you'll get a little insight into what both of those choices can look like. So let's talk about, before we even mention quantum physics, what types of physics are there? How do we define fields in physics? First, we categorize by speed and by size. These are two metrics or two measurements that are critical to understanding what you're doing in physics. So we have this nice diagram, a 2x2 diagram. In the top left, we see classical mechanics. So this is where we are pretty slow and we are not tiny. So normal life lives in classical mechanics. When we throw a ball, when an apple falls from a tree, when we go for a walk or ride a bike, that we describe as classical. Like classical music, traditional. It's the physics that has been around for hundreds, if not thousands of years now. We understand classical mechanics. It governs everyday life. But what happens if we get really fast? What if it's still everyday life, but somehow we have this biker pictured and he starts going really, really fast, nearly as fast as light? Then we start dealing with a totally different type of physics, and we describe this as relativistic mechanics. Relativistic, relativity, it's a word I will use, and it just means things that go really fast. If things go really fast, physics changes completely. Our understanding of mass, of weight, of movement, really of reality, changes completely when things go really fast, especially as things approach the speed of light. So that's our speed axis, but also we can talk about size. So if we start from classical mechanics and we have this biker, but now this biker gets really, really small. He still moves at the same normal speed, but he becomes very, very small. We now need new physics again to describe him. We would call this quantum physics or quantum mechanics. When I say quantum, it means really small. And that's why I said I viewed quantum physics as a first step. When we talk about particles or light or really small things, they're governed by new, interesting phenomenon, which we call quantum physics. Then in the bottom right corner, you'll see quantum field theory. That's very high level. Now we're very small and we're very fast. It's horrible. When I say horrible, I mean extremely complicated. This is also the best way to describe life because light, photons, electrons, it's very small and it's very fast. And so we have to understand this quantum field theory in order to know more. So we'll get more into quantum physics and quantum mechanics later, but think small. That's what we're talking about. Things that are very small and probably very fast. Of course, we have many subfields after this. You may have heard of these. I won't go into each of these, but if you're interested in physics, please look into them. I tried to, again, start at the really big, astrophysics. It deals with space and with planets and the universe. That's really big. At the bottom, we see quantum physics. Like I said, really small. Between there, you have solid state, biophysics, plasma physics. We won't get into those today, but we have many subfields within our profession or within our field. So what is quantum physics? I said before, it's small things, and it gets really interesting. Really, quantum physics, I say, explains everything, because that is what it sets out to do. By describing the smallest things, we describe the most true results, or the most true equations, most true laws of nature. And the most true laws are exceedingly surprising. That is maybe the theme of quantum mechanics, is it's hard to learn and hard to understand because the results are shocking of how we, as we understand it, the world works. So physics is really not that accurate. Quantum physics, or really small physics, shows the limitations or the flaws of classical physics or classical mechanics. Newton's gravity, or force equals mass times acceleration, really helpful equations for daily life, for throwing a ball, for riding a bike, and all of those things. But in fact, not very accurate. They don't explain the natural world accurately. They are approximations. They are estimates. They are so useful, but not that true, not that fundamentally true. Quantum physics strives to find the most true explanations. At extremes, and I say here really fast or really small, our equations or our intuitive, our known understanding, our known equations fail really dramatically. If we use classical equations for really small objects, it makes no sense. If we use classical equations for really fast objects, it's completely inaccurate. And so quantum physics tries to find the more true or the more fundamental laws or rules. Quantum physics looks at small objects. By describing the smallest objects, quantum physics can or tries to explain everything. Chemistry, biology, everything in the world is governed at the smallest part, or is controlled at the smallest part, by quantum physics. And so, for me, that was the interest in it. We must understand quantum physics to accurately describe or accurately explain how human bodies work, or how medicines actually work. It is all based on quantum physics. We primarily work with atoms. On the right here, you'll see an atom, or a depiction of an atom. We work with electrons. Those are the minus symbols you see. Those are negatively charged, very, very small particles, and especially light. When we talk about quantum physics and quantum mechanics, we are really interested in light, in electrons, in these really small things that can be really fast. But things being small, turns out, presents a lot of difficulties. In fact, everything is so small that we never really know precisely everything about it. And this is a fundamental rule. First, we must talk about what's called wave-particle duality. This is essential to understanding the small universe that we have. On the left, you see a wave. A wave might be in the water. A sound wave is how we hear waves. On the right, I've depicted a little ball, but that is how we can think of a particle. Particle is not a very well-defined word. It just means something that is definite, that has size and shape and is right here. This is a particle. So a long time in physics, in classical physics especially, we classify things as waves or as particles. So we think about sound. Oh yeah, sound, that is definitely a wave. It travels in the air, it goes into our ears, we receive it as a wave. Underneath the water, you can see how we often depict waves in physics. And in classical physics, we think, okay, sound is a wave, and light or electrons, those are particles. Those are definite sized objects. Well, it turns out one of the most shocking and still difficult to understand results is that is not true at all. Light and everything in our universe, as we understand it, is both a wave and a particle. We call it duality. At once, every object in the world is a wave and a particle. In classical world, we never knew that, and we didn't care. It did not change our results. A person on a bicycle is so big that their existence as a wave and a particle essentially the same. It does not change any of our understanding. However, when you get small, this becomes critical, super important. I've shown on the left, below the water, we have this wave. We might call it a wave packet, like a group of waves in physics. And actually, this represents a sort of probability. We can think of it of over what space an object exists. And so when we say light is a wave, or an electron can be shown as a wave, it actually has a probability of existing in this whole wave region. And some way to understand wave-particle duality is if we squish this wave together, if we know more precisely the location of something, then all of its probability is at one point. We have this on the right side here, which looks like a straight up and down line. In truth, that's still a wave. It's a strange looking wave, and it's so strange that we call it a particle, but still it has the behavior and the properties of a wave. And so when we think of particles, we think of waves that are very definite, that are small in extent. But everything, light and everything else, is a wave and a particle. We use this all the time in quantum mechanics. All the time. And it ties into the Heisenberg uncertainty principle. It's hard to overstate how critical and fundamental this is. So fundamental, so basic as a rule, it's hard to explain properly. The basics. Some values cannot be known exactly at the same time. There are some values that just don't fit together. By values, I'm talking about things like the value of a human is the height and the weight and any of those things. When we talk about particles or small objects, some values don't fit together. We can't exactly know both of them at the same time. For example, the most crucial example, speed and position cannot be exact at the same time. It is impossible for us to know exactly where a photon, that is a particle of light, exactly where a photon is and how fast it is, or exactly where an electron is and how fast it's moving. This principle is fundamental, it's basic, it's critical, it's important, but it's also confusing. So let's use an analogy to try to understand it. We will talk about cars and photographs. So here is a picture of two cars. It's a picture that was taken quickly. The lens of the photo snaps quickly. And so we see the two cars. We can describe their position exactly, really, really well. We know where the first car begins and stops and where the second car begins and stops. But this photo, it tells us nothing about their speed. You can try to make a guess, perhaps, but we will never know exactly how fast these cars are moving because this photo was snapped in such a way that it gives us insight into position, but nothing about speed. That shows you that these are somehow values that don't fit together, that don't work together. In this photo, we might call it long exposure. The aperture or the lens, we took the photo and it stayed open for a long time as the photo was snapped. As a result, we have some blurring, almost like these cars are waves, right? Almost like these cars are extended over more space. And so if we know the speed of our camera lens and we measure the positions of these cars, we can calculate speed. We will know how fast these cars are. But in this photo, we don't know. There's no such thing as position, as exactly where the car exists, because it's sort of like a wave extended over space. The Heisenberg uncertainty principle. There is uncertainty in everything in quantum physics. It is difficult. So even if we know everything about an electron, we can never know exactly its speed and its position without measuring it, which becomes a whole problem of itself. So I want to talk about some of the strange quantum behavior. This is the really unbelievable stuff, and I'll only touch on each of them, but this is how we believe the world works at a fundamental level, and it's crazy. And it's really interesting and opens the gate for a lot of new and interesting technologies. So let's first talk about quantum superpositions and the measurement problem. Quantum superpositions and the measurement problem. I said that we can never know an electron's speed and position and all of its values without measuring it. So what is the measurement problem? To understand this, we can look at a very popular thought experiment, a sort of puzzle by Schrödinger, the same physicist who will be critical to quantum physics. Schrdingers Cat and the measurement problem. In this little cartoon, we see there are two situations that exist at the same time. One in which there's the cat dead on the floor. There's this poison that has been released and killed the cat. And there's the switch that released the hammer to release the poison to kill the cat. This we might call the dead cat situation. But there's also the alive cat situation. In the alive cat, the switch was never flipped, the hammer was never dropped, and the poison was never broken. And so Schrödinger says, how do we know, or when do we know, if the cat is alive or dead? If the cat is in a box, is it alive or dead? Do we know, can we know before measuring? And in my opinion, this thought experiment is a little silly and a little inaccurate, but it's really helpful to think about quantum physics. Let's talk about electrons.
So PJ, if you don't mind my saying really quickly, in fact, Schrödinger would agree with you, because the reason he came up with this thought experiment was because he wanted to show how absurd these sort of theories are. How can something be two things at the same time? But little did he know that this would be the basis of new technologies so many years later.
Totally, exactly. And so what Ujjan is hinting at is this is almost correct. If we think of electrons, we can say they have spin, some abstract or any quality, and let's say it's up or down. And we don't know whether it's up or down until we measure it. And what is it when it's not measured is the question. before it's measured, how do we describe it? Do we describe it as up or down? And the real answer, and what we call superposition, is that it is both. Is that quantum objects can have both qualities at the same time. So if we talked about it as a cat, it would be both alive and dead. We would only know or make a decision. We would force a decision on the universe by looking in the box. And so people might say, by looking in the box, you kill the cat because you force it to choose alive or dead. And this is a real fact of nature. When we observe or measure quantum objects, we force them to choose an option. Before they choose, before we measure, they are legitimately both alive and dead. That is critical to all of quantum physics. Also hard because measuring, we say superpositions, they are delicate. We can mess or change a very intricate, very complex superposition by measuring, even if by accident. All of a sudden, it has been decided. Suddenly, we force it to decide if it is up or down, alive or dead. Ujjan will talk about a little how this plays into technology and how quantum computers use this, as will I. Measuring is a problem. Superposition is critical. Electrons are alive and dead. Next, this is my favorite one. That's a lie. This is my second favorite one. We call this quantum tunneling. And this is a sort of very surprising. And I said, walls aren't as solid as you think. Quantum tunneling is the phenomenon or the occurrence that quantum objects, or I say collections, groups of quantum objects, that means anything that's really small, have some probability of transferring some parts through a barrier or through a wall. Probability, some uncertainty governs quantum physics. It's really hard to tell in exact numbers how much will pass through a wall. But let's look at this graphic, this little picture. This is photons, so light hitting a barrier, a very thin barrier from the left. And we see that there is some dim, or not bright, but there's some light on the right side. This shows that some of the light has transferred through a solid object. To put it into plain English, but this is an exaggeration, there is some probability that you can walk through a wall. If you walk straight into a very, very, very thin wall, there is some probability, it's possible to walk through it. It would take like quadrillions, unbelievably big numbers. It's so unlikely because of how big we are and how many quantum objects are in us and how big a wall is. But with small objects, it happens, as we see here. Quantum objects can move through walls. And it's just about waves, and it's just about probability. But it's shocking and surprising. And it's fun as a fact. This is actually my favorite one. And this is the foundation of the most exciting quantum technologies. And it's called quantum entanglement, or as Einstein called it, spooky action. Spooky as in scary, as in confusing, because it is scary and confusing. Two quantum objects, let's say it's electrons or maybe it's photons, they can be paired. They can select each other, and we might call it paired. They are a pair. This pairing is extremely strong, extremely strong. And coupled or together with the measurement problem, it creates really interesting scenarios where measuring one of the electrons collapses both of the electrons instantly. When I say collapse, I mean it forces them to decide if they are up or down, alive or dead. So, paired quantum objects, they are in a superposition. They are both up and they are both down. And they're in every combination of up and down and up at the same time. However, when we measure any element of this pair, everything is decided. It collapses along its element. We say along the axis, but basically, I have two electrons. I don't know if they are up or down, or which is up or which is down. They're both. But if I measure one and it's up, I always know what 2 is. I have already decided. And if we measure 2, I will always be right. So, by measuring particle 1, you know about particle 2. Across, it seems, any distance. How does particle 2 know when particle 1 is measured? Great question. That is what Einstein described as spooky. When we measure particle 1, why or how can particle 2 learn that particle 1 was measured? There is quantum entanglement. These particles are connected. They share information. Their total situation is decided by either one of them. Coupled with the measurement problem, this is really, really fascinating and very strange.
PJ, do you mind if I add something to this?
Please.
So there's a little bit of a subtlety here, and PJ did a really, really good job explaining it. But there's one thing I want to point out, which is that he mentioned that this sort of pairing exists at any arbitrary distance. And this is true. And he also mentioned that that arbitrary distance could be, at the edges of the universe. So say PJ is measuring his electron at one edge of the universe, and I am measuring my electron at the other edge of the universe. And somehow these electrons are entangled. They were built that way, say, such that when this is up, my one will be down. When my one is up, this one will be down, something like that. Interestingly, when PJ is measuring it, he doesn't know what I'm measuring because I'm so far away from him that he cannot send me information that is faster than the speed of light, so that he can't call me and we can't have a telecom fiber connecting us so that I can get the signals, and we can't instantaneously know what's happening. So we are not actually breaking the speed limit of the universe, which is the speed of light. We are restricting all our communication to the speed of light. It is only after PJ does his experiments and I do my experiments, when we come back home to Earth and we compare our results, we find out that this thing has taken place. Every single time he measured up, I measured down, and vice versa. And that is what was so spooky to Einstein. How can that happen? Nothing travels faster than the speed of light, so this information shouldn't travel faster than the speed of light. But he missed something. Even Einstein missed something, believe it or not, which was that nothing is traveling at the speed of light. These correlations exist, and then we come back, and when we talk about it, we realize that they exist. But we came back slower than the speed of light. We talked slower than the speed of light.
Mm-hmm. Yeah, totally what Ujjan said. A confusing nuance. The rules aren't breaking, but it feels like they are. And because it feels like they are, it actually opens up a lot of technological possibilities, which we get into now. Quantum technology. We have all these crazy theories. How will it actually be useful? What will we use it for? So first, what makes quantum technologies interesting? 1, speed. Quantum technologies can be very fast. 2, strength. They can do huge problems. And 3, efficiency. They can do them at low cost, energy-wise. So first, let's just talk about quantum computers, and then I'm going to let Ujjan take the floor on his presentation. The basics of quantum computers. First thing to say, they cannot replace classical computers or computers that we have. Quantum computers are totally different. They work on completely different information, logic, everything. They are so good at specific problems. So classical computers, they use transistors, or that is their unit that they build on. Quantum computers, we use smaller objects. We use electrons or photons, light. In classical computers, information is 0 or 1. 0 or 1. You have two options. In quantum computers, information is 0 and 1. Because of the measurement problem, because of superpositions, we are always both. That allows for insane combinations of states or of situations. We can express a lot of information. Classical computers work in sequence. We do part A, then part B, then part C, then part D. Quantum computers, because of the way electrons are entangled or our system is built, we do all of our calculations kind of at once, parallel, we might call it. This makes them incredibly fast. And because the electrons all communicate with each other, the power or the speed of our quantum computers increases exponentially in proportion with our quantum bits. So they get very strong very fast. If I have 5 transistors and I add a 6th transistor, my computer isn't much more powerful. If I have 5 electrons or 5 qubits and I add 1 qubit, I now have a completely different machine, capable of totally different projects. And so here, I will let Ujjan take over and talk a little bit about his project and his research, and talk about how he's using these phenomenons of quantum physics. So, Gulshan, if you could let Ujjan's screen show now, that would be great.
Yeah, PJ, could you just let me know if you can see my screen?
We see it in a small form, not fully presented mode, but it works.
All right, let me reshare if that's okay.
Yeah, of course. And so what Ujjan works with is quantum information. And so it's using this entanglement, and it's using quantum information and quantum computers. And how do we build systems with that? How do we take advantage of these quantum phenomenon? And that is the problem that Ujjan, as a PhD student in physics, works on. And he will talk about his research.
So, PJ, do you still see it in the way you were seeing it before?
Yeah, I do. But I think that this works if you want to flip through the slides this way.
Okay. I'm sorry about the problem with the sharing, but I'm just going to continue with the presentation if that's okay.
Please do.
Right. So PJ mentioned how things in the classical world, in terms of classical computers, work in a very different way from the things in the quantum world. And he said that classical computers use something called bits. So bits are things that can be 0 or 1, as he mentioned. So something that is a bit is a transistor. So whether you have current flowing through a transistor or not determines whether that transistor is going to be in the state 0 or going to be in the state 1. So if current is flowing through the transistor, we say it's in the state 0. If it's not flowing through the transistor, we say it's in the state 1. Or, that can be flipped. It doesn't really matter. In quantum mechanics, if we want to use quantum mechanics to build a quantum computer, for example, we need something that can be both 0 and 1 at the same time, and that mathematically is represented by this sphere. So it's this kind of a ball where the north pole of the ball is, say, 0, and the south pole of the ball is, say, 1. And being a mixture of 0 or 1 or a combination, or the word that PJ used was superposition of 0 or 1, means that you can be anywhere on or even inside the sphere. So you have an infinitely greater possibility or infinitely higher number of places where you can put your information, where you can store your information. Yes, when I want to measure this information, as PJ mentioned, my state is going to collapse to either 0 or 1. However, before measurement, I have all this space anywhere on or even inside this ball to store my information. So, scientists have been thinking, what can we have that is going to make a good quantum bit, or a qubit, as they like to call it? And some scientists have come up with very, very interesting designs about using similar materials that actually classical computers use to make semiconducting qubits or even superconducting qubits. However, my research is more involved with something that we don't have to build, something that comes to us naturally. As PJ mentioned, that thing is light. And specifically, single particles of light, tiny little small particles of light, known as photons. So now the next question, of course, is what is a photon, and how do we get this 0 and 1 in a photon? Isn't it just some kind of a tiny little fuzzy ball that we can't really see very well? Wait a second, how do we even see photons? I thought we use light to see things. And if photons are light, how do we even see light? Well, these are all very good questions, which my group at the University of Illinois in Urbana-Champaign is investigating and using to build technologies that are going to change the way we do our computations. So how can we use photons as qubits? So here I've drawn a photon as a little sphere. Normally, mathematically, you can't really describe it so nicely as a sphere, but just for the sake of this diagram, I've drawn it as a sphere. And here it's traveling along this direction in the x-axis. And this wiggly line represents the electric field that it generates. And as you can see here, the direction of the wiggle, or the direction of the oscillation, is along the y-axis. So it's up and down. And we call this oscillation, or this direction of oscillation particularly, we call it vertically polarized. Similarly, if that direction of oscillation of the electric field due to the photon was along the z-axis, we say it's horizontally polarized. So this is fundamentally different. In one case, the photon is vibrating up and down as it's going along the x-axis. And in the other case, the photon is vibrating sideways as it is going along the x-axis. So this could represent our 2 degrees of freedom, as we like to call it in physics, of 0 and 1, or of vertically polarized and horizontally polarized. As in the previous diagram where we saw the vertically polarized, or the 0, was the orangish color, and the horizontally polarized, or the 1, is the bluish color. And the whole thing about quantum mechanics is that we need superpositions or combinations of 0 and 1, or vertically and horizontally polarized, or as PJ pointed out with the example of Schrodinger's cat, dead or alive, which is always very nice to talk about and kind of think about. But these are much easier to understand for me. And what we want is we want to get these photons isolated, to get them at a single particle level existing in these combinations, so that we can use them to store our information and do computations using quantum computers. So the question is, we know that photons are everywhere. You switch on the light, you have millions of photons. You even light a candle, you get 10 to the 19 photons that come out. So how do we isolate photons to be just one single photon that shows just a few properties that we need to use for quantum mechanics? And that's where our project comes in. We create single photons using a process called spontaneous parametric down conversion. Another very fancy physics term, and it's easy to forget, so I'm just going to write SPDC. And this process uses some kind of a crystal which when light is sent into the crystal, splits that light. So if it's a little pulse of energy, it splits that energy into 2 paths. And each of these paths contain the energy equivalent of one single photon. And we call one of those photons the signal photon and the other photon the idler photon. And interestingly, this is where superposition and entanglement become very important. So as PJ mentioned, you can have particles that are entangled. And the particles, the 2 particles or the 2 photons that are produced in this process are entangled. Whenever I have the signal photon, I do have the idler photon. Now, this process doesn't always generate signal and idler photons whenever I want them to, but when it does generate the signal photon, it also generates the idler photon. So that's the entanglement that's happening here. And this thing, this semicircle over here, is a detector. So when I detect my signal photon, I know that my idler photon is in the other path because these 2 are quantum mechanically entangled. And so then I can send it to this storage loop, and it can run around in circles until when my quantum computer needs it, and it calls it, and then I release my single photon. So currently, the technology that my lab has been working on has this working at a rate of 67%. So 67% of the energy that we send into it is converted into a single photon. However, for real-life quantum computation applications, we need this to be much better. And that's where my job comes in. My job is to make this storage loop, actually, specifically in this whole experiment, much, much better so that we can drive up this efficiency to maybe 75, maybe 80%. And so I need to make this better. And the question is, how do I make it better? And I actually need to come up with something that can change the polarization of the light. So in the previous slide, we saw vertical and horizontal. So I want to change that as quickly as possible, maybe at the rates of 10 to the 9 times per second. And why do I need to do this? Just to recap, I need to do this so that I can get the single photons when I want them. Recall that I mentioned that this SPDC process is not happening when I want it to. It's happening when sort of the crystal, this little box here wants it to. So I need to battle against that. I need to make sure that I get it when I want it to. And for that, I need this process in the storage loop to happen much more quickly than it does right now. So other interesting work that is going on in my research group is that we are trying to do quantum communication between drones flying in the air. We are also asking the questions, can humans even see single photons? How are our eyes good detectors? We are generating different sources of quantum entanglement using photons. As PJ talked about quantum entanglement, it's that very same thing. We are studying quantum communication from space to Earth, between the satellites in space and our ground stations in Earth. And also we are looking at quantum imaging, quantum telescopes, and much, much more. If you're interested in our research or in finding out what we do, more about what we do is available on our website called the QIAT Quantum Information Group. So feel free to head on over to that if you do want to. And with that, I'll hand it over to PJ.
Yeah, Gulshan, if we could just show my slides one more time, just for a minute, and then we can take questions. Perfect. So Ujjan talked about how uncertainty makes quantum computers difficult, and even getting like quantum qubits so difficult. It's his whole job. So why do we need quantum computers? Here are just 2 examples of why they'll be useful. In new medicine discovery, like I said, quantum computers can do a lot of things at once. We can test all different structures and all of their reactions with humans and with molecules at the same time. So in business, pharmaceutical companies or medicine creators are investing a lot in quantum computers to help discover new medicines much, much, much faster than we used to be able to. Also, this big one is a huge conversation in cybersecurity. You can create incredibly secure and complex quantum passwords. This is a dream for governments, for big companies, anything like that. More scary, and a conversation that I've had a lot in the business world, is cracking typical passwords, or like solving or hacking into typical passwords. You can do it extremely quickly with certain quantum formulas or certain computations. So I said that quantum computers can do everything at once, or some variations of them can. So, for example, they can guess all the series of 16 numbers or 16 letters at the same time. For a normal computer, that might take days. For a quantum computer built correctly, it could be instant. And so that makes typical passwords extremely insecure. So that was an overview of quantum physics, just touched on quantum technologies, and we'd be happy to take any questions, Gulshan, if there are some in the chat.
Thank you so much. That was so interesting. A very complicated topic that both of you were able to make it understandable for us. So yes, we have some good questions. So first question is from Odil Dilmorodov, and he's asking, what was the most challenging thing in the university as you didn't know physics?
Hi, Odil. He's a volunteer at the American Corner Karshi, really interested in physics and math, and so I'm glad you asked the question. Starting physics for me was quite difficult. Having a foundation in math, or like I had studied quite a bit of math, made it easy. But maybe a silly answer. When I first learned physics, people had some prior experience, and I think other people were much better at using the real world to understand the physics. And so, you know, mechanics problems where we just throw a ball, we think, oh, well, how would it work intuitively? I was never a good intuitive thinker, and I was rather stubborn. And I said, our intuitive thinking, it doesn't actually explain physics. And quantum physics speaks to that. It's not intuitive at all. Nothing works how you would think it works. And so for me, it was having a foundation in math. And to be honest, I love physics textbooks. People like Griffiths is a very popular textbook writer. So I worked with Ujan a lot. I studied math, and I used good physics textbooks.
Yeah, I must say for me, like for PJ, it was having others. For me, it was having PJ, honestly. Because he helped me so much to do a lot of my homework. Sometimes, you know, we wouldn't understand, and we would stay up till 2, 3 a.m. discussing these things. It was a good time, honestly.
Great, thank you. So next question is, how did you come up to the idea that you want to study quantum physics? What made you study it?
For me, it really was stubbornness. I said, I want to know everything. How do I know the most basic that can explain everything else? And so that is as far as I went. And I thought, okay, then it seems like I should know about quantum physics, which explains the smallest things. And that was all of my reasoning. It was not any more interesting than that. Ujan, how did you arrive at quantum physics?
Well, I wanted to study physics in general because I thought, you know, it'll give me some sort of a truth of the universe, what's happening around me, answer all these big questions that I have. But when I started to study quantum physics, I realized that there is a great deal of things that we just don't understand and that we cannot intuit as human beings. And that, to me, is just a bigger truth than anything else, that we don't know what truth is. And in many ways, that sort of fuzzy feeling that I got, that, oh, wow, we don't understand this well enough. Maybe I should try and understand it just a little more than we already do, is really what makes me want to study quantum physics.
Wow, thank you. All right, next question from Daniya Hasanova. You mentioned that sound waves are part of the quantum physics. Why some people hear words differently, like Laurel and Yanni?
This is funny. I don't have a good answer for you. I haven't studied this specifically, but certainly recently it's been very popular of colors or sounds that people hear differently. And it's not a coincidence that both of those are waves. When you see something, it's processing light waves. When you hear something, you're processing sound waves. waves are the same. I had a professor, a whole class on waves, and he said everything in life is a wave. And a wave is a wave is a wave. Every wave is the same. And so our eyes and our ears have their own systems for understanding waves, but they both are made to process waves. And so due to the biology of individuals, there's some differentiation or some difference in specific words. I don't know more than that to answer. Ujan, do you have insight on Laurel and Yanni?
This is a very interesting question. I don't think it's necessarily answered by quantum mechanics, but it's definitely interesting to think about. And I think what we can take from it in terms of quantum mechanics is that the whole idea of the measurement problem, right? The measurement kind of influences the result itself. If you hear Laurel, you'll go back to your lab and say, I heard Laurel. And if someone else heard Yanni, they'll go back to their lab and say, I heard Yanni. And so in many ways, you can say it's in a superposition of Laurel and Yanni. Although it's not.
All right. Thank you so much. What would you do if you were not doing quantum physics?
Yeah, well, good question. Right now, I would say I would go to Uzbekistan and teach English and open the American corner factory, which is what I'm doing. But I said that I started studying physics and quantum physics because I wanted to know everything. And I stopped in part because the project is just so big. To build working quantum devices, or like Ujan said, we don't understand everything or anything really. As a young person, I thought physics is beautiful. You know, everything works and the universe is magic. But the more you study physics, the more it seems broken, like totally random and makes no sense. And so I decided that another avenue for me to learn as much as I can would be to travel and to teach and to learn that way. Yeah. Ujan, what about you? Do I see your guitar in the background?
Can you see it?
Yeah.
Yeah, it's right there. Yeah, for me, if I wasn't in quantum physics, I would probably be doing something to do with music. I love music. I play guitar and piano, and I sing. And you know, if I had a little bit more time, maybe I would do more of that. But don't tell my professor I said that.
Yeah.
Yeah. Maybe we can do a chat on music sometime, Ujan.
Yeah, I'd be happy to talk about it.
Yeah. All right. Unfortunately, we have to wrap up, and looks like we got a lot of people saying hi and saying that you guys have a lot of talents and thanking you for this wonderful presentation. Yeah, fantastic presentation. So thank you guys so much. It was very interesting. For me, I don't know about others. For me, it made me learn more about quantum physics because I knew nothing about it, but now I understand something and want to know more about it. Thanks so much, and I hope we'll see you, both of you, someday at our other chats.
Thank you so much. Thank you
so much for hosting, Gulshan, and thank you, Ujan, especially for coming and waking up early in the morning in Chicago or in Illinois and doing this.
Yeah, thanks for inviting me, PJ, and thanks, Gulshan, for organizing this.
Yeah.
Thank you, guys. All right, have a good weekend. Bye-bye.
Bye-bye.
Bye-bye.